So we'd like to discuss how we can come up with an equation of a plane in space. Now there's a few different planes that we've already talked about. For instance, in the three-dimensional coordinate system, the XY plane is the flat plane that represents the floor, say, of a building. But then we ended up having the YZ plane and the XZ plane that tended to be sticking up in the air as if they were walls. But what about planes that are just random pieces of paper that are slicing through space? How could I come up with the equation of the plane that's just slicing through at a particular angle? So that's what we're going to investigate today. We're going to come up with some equations, and we're going to come up with a couple of applications involving planes. So let's just say that we have a plane, and we know a point that's on the plane. Unfortunately, it's not enough to just know a point on the plane, because we have to know some other point on the plane as well. Let's just say that we ended up having another point that extended to, let's just say that we had another point out here called P. Then notice that there is a vector that I could draw from P0 to P. But you might notice that just because you have a vector doesn't mean you have a plane. So notice that there's lots of different directions that I could take off in from P0, all of which are going to end at various locations in the plane. But notice that depending on the direction, I still can't tell what the plane is because these may have all kinds of weird angles. This one right here might be actually pointing down below the plane. And this one right here might be pointing up above the plane. So let's just keep in mind that really, if we have a vector in the plane, then it's difficult for us to be able to tell what the equation of the plane is going to be. But what if we had a vector that was normal to the plane, to where it was orthogonal to the plane? Let's call that vector n. Well, you might remember back when we were talking about cross products, the vector n is describing the tilt of the plane. So we're going to be able to use the tilt of the plane, that vector that's orthogonal to the plane, in order to calculate what the equation of that plane is going to be. Well, in order for this to be, or in order for n to be orthogonal to the plane, let's just take a look at all of the vectors that are in the plane. Let's pretend that all 4 of these vectors are in the plane. Why don't we get rid of the vector n where it is there, and let's move it to touch P0. And now if I look at vector n, I should recognize that this better be orthogonal to every single vector that's in the plane. So in order to come up with an equation for a plane, if we happen to be given some, random particular point, let's call this the point x0, y0, z0, of course. And point P would be the point x, y, z. Then what we should recognize is that the equation of the plane, okay, or rather let's call this maybe vector, but maybe let's call this plane M, okay. M is the set of all points which we'll call P, such that the following is true, such that n dot P0P has to be equal to 0. If you don't remember about dot products, that might be a little peculiar, but what does that mean for n dot P0P to equal 0? Anytime the dot product is equal to 0, it tells us that the 2 vectors are orthogonal. So what that's telling us is that I know that the plane must be true, or I must have a plane, if the vector sticking out of the plane is orthogonal to every vector that extends from P0 to any point in the plane. And so really all we have to do is calculate the dot product between these two vectors. So let's just label n as being the vector ai plus bj plus ck. So let's just say that we have a normal vector. I don't know what that normal vector is, but any normal vector would do. And flash forward, how about the cross product? So we're going to be able to use a cross product oftentimes in order to find a normal vector, but sometimes we'll be given a normal vector that's normal to the plane. And so at this point, let's just set up that equation, okay? That must mean that the dot product between these, that if I multiply ai plus bj plus ck, if I take the dot product between that and the vector p0p, which remember would be x minus x0i plus y minus y0j plus z minus z0k, then that dot product, in order to get a plane, must equal 0. So now it's just a matter of calculating the dot product using our dot product formula. If we calculate using our dot product formula, we just multiply the I components, the j components, and the k components and add them together. So that means that we're left with a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. And that right there is what we refer to as an equation of a plane. That is the equation of a plane, where a, b, and c are nothing more than the normal vector to the plane. So the coefficients of a, x, y, and z are going to be the normal components, or the components of the normal vector, or the vector orthogonal to the plane, while x0, y0, z0 is any point that's on the plane. Now, why don't we move things around a little bit here? Why don't we distribute and get ax, distribute the b to get by, and distribute the c to get cz. But then we'd also have these other terms subtracted. So we would have ax0, by0, and cz0. So let's go ahead and move those to the other side. Now, the reason why this is important is because this would all be given. We would have been given the normal vector. We would have been given the initial point. So this right here is a scalar. So in general, the equation of a plane, will always be in the form of ax plus by plus cz, which already kind of looks like a linear equation, except it's got an extra variable, right? So they're all linear terms. They're all first powers. And so it looks like if I want to create an equation of a plane, I just need to write ax plus by plus cz equals some constant, where that constant is the scalar right here. So in practice, this right here, this form is typically the form that we would use in order to create the equation of the plane. Okay? But it simplifies to this. And there we have it. So that's what we're going to use in order to come up with the equation of a plane. So looking at our first example, What if we were given 3 random points in space and we wanted to find an equation that had those points? Well, I've gone ahead and plotted these points on a 3-dimensional coordinate system just so we could visualize what's going on here. But you should be able to see that if those are intercepts on the x, y, and z axis, then you should be able to see some sort of plane that cuts through in order to create that plane. So there's some plane that has those 3 points involved, okay? And so in order to find the equation of the plane, keep in mind what we need. We need a normal vector to the plane, and we need a point on the plane. So that's pretty much all we need, right? All we need is the equation, or is a normal vector, and we need a point. So let's write out the form in general, okay? The form would be a times x minus x0 plus b times y minus y0 plus c times z minus z0. Now when we talk about x0, y0, z0, that's equal to 0. When we talk about x0, y0, z0, all that is any point that we're given. So we virtually could use any one of the points we want. So why don't we just use the first one, and we could start off by saying that this is a times x minus 0 plus b times y minus 0 plus c times z minus 1. I just chose to use the point P. But now what we need is a vector ABC that's going to be orthogonal to that plane. Well, the only type of vector that I know that I could find that's orthogonal to a plane is a cross product between 2 vectors. So just like we did in a previous type of example, if we have 3 points, we could find vectors involving those points. So what if we were to look at this vector, PQ, and then we look at this vector right here, which would be PR. So if we find those 2 vectors right there, or look at those 2 vectors, we could find a cross product, which would essentially just be the vector that's sticking out of this plane that's going to be orthogonal to both of the curve, or both of the vectors. So that's why it's helpful, even though I'm not expecting that you always graph everything in the class. I think it's helpful to actually visualize what's going on so you can come up with some sort of game plan. So why don't we start off by finding vectors PQ and PR. Okay. So vector PQ is just the difference between each of those vectors. So PQ is the vector 2 minus 0, 0 minus 0, 0 minus 1. We also see that PR is going to be the difference between each of those components. So we see 0 minus 0, 3 minus 0, and 0 minus 1. So now that we've got those 2 vectors, PQ and PR, we can find a cross product which will act as our normal vector, the N, the ABC that we need. So in that case right there, we simply find the cross product between PQ and PR. Because that is going to represent our normal vector. PQ cross PR is normal to the plane. So let's set up our determinant. So I, J, K, and then we put PQ 2, 0, negative 1, and PR 0, 3, negative 1. And when we simplify, we end up getting our components. So for our I component, we get 0 minus negative 3, which is 3. So we get 3i. Minus. Now in our j component, we get -2 minus 0, so minus -2j, so plus 2j. And finally, in the k direction, 6 minus 0 is 6, so we get plus 6k. And that is what represents our normal vector. More importantly, that simply represents our A, our B, and our C. So the equation of the plane is simply 3 times x minus 0 plus 2 times y minus 0 plus 6 times z minus 1. And if we expand and simplify, this gives us 3x plus 2y plus 6z equals, and now the -6 moves to the other side to give me our answer of 6. So what's beautiful about this is to recognize that once you know a normal vector, those are literally just the coefficients of x, y, and z. All I need my initial point for is to be able to find what that constant on the other side is. And I really could have used whether it point P or point Q or point R. Any one of those I chose to use, I still would have gotten the constant of 6. Well, I'd like to show a couple of consequences about equations of planes and about how we can understand when two planes are parallel and what happens when two planes intersect. So we see a few different planes that are on the page here. We see the blue one and the orange one. They end up intersecting at some place. And when two planes that are not parallel, intersect, they'll intersect in a line, which is what you see for this purple line. Now, one thing I do want to recognize, or what I do want you to recognize here, is that the orange and the green vectors, or the orange and the green planes are parallel, but they're only parallel because their normal vectors are parallel. So let's just say that I end up taking a point right here in the orange one, and then I look at its normal vector. Let's call that N1. Well, if the vectors cross product in the green one also has a particular normal vector, which we'll call N2, they may not be equal, but I know the two vectors are parallel when their cross products are parallel, or when their normal vectors are parallel. Okay, so I'll just write that down here. Two planes are parallel if and only if their normal vectors are parallel. So really, it's getting back to lines and vectors again. So instead of just simply saying two planes are parallel because they're flat and they never cross, instead we take their normal vectors and now we just compare the slopes of those lines. And if we know that N1 is some constant multiple of N2, then I know they're parallel. But what if the two vectors or the two planes are not parallel, like the orange and the blue vectors, or the orange and the blue planes rather? How exactly could we find the line of intersection of the two planes? Well, there's one very interesting component to this as well. Let's say that we have a normal vector to the orange plane. Remember, normal vectors could be popping out of anywhere and they could be any length, right? They could be upside down, just like N1, or they could be popping out vertically. There's lots of normal vectors, okay? let's say that that right there is one of the normal vectors for the orange one, okay? Which obviously would be, here's a point in the orange plane, and there's the normal vector. Well, now what we want to do is find a normal vector for the blue one. Let's say that the blue one has this normal vector. Okay, so the blue one has this normal vector with this point that's at the blue. So what this means, remember, is that each of these is going to form a right angle to the plane. And this will form a right angle to the plane. Well, what we would notice is when we look at the line of intersection of the two planes, since the line of intersection is on each of the planes, we should also realize that that line of intersection will be perpendicular to each normal vector. So if we were to call this normal vector, let's say N3, and let's call this normal vector up here N4, we should realize that both of those normal vectors are going to be perpendicular to the line of intersection of the two planes. But more importantly, they will also be perpendicular to the line of intersection that ends up passing through where they meet, which tells us something really, really special. This purple line of intersection of the two planes is perpendicular to each plane's normal vector, which is why we can see that N3 is perpendicular and N4 is also perpendicular. But what that also must imply is that the line of intersection is parallel to the cross product between N3 and N4, because the cross product is perpendicular to each one of them separately. So if I think of N3 cross N4 as being this cross product right here between the two vectors, then I could see that the line of intersection, which we could call L, I suppose, is parallel to that cross product. So that's just something pretty interesting, so we can actually use that in this next example. Let's start deciphering in this problem what we have and what we're going to need and what we're being asked for. So it's first of all saying find a vector parallel to the line of intersection. Well, based on our diagram we just saw earlier, a vector parallel to the line of intersection of two planes is just going to be the cross product between the two normal vectors of those planes. And we should recognize that if we are given a plane right here, then we could find what one of the normal vectors is, because I know that that's just the coefficients of 3, -6, and 2. And I could see that if I'm given a second plane, then N2 is just going to be the coefficients of that plane, which is 2, 1, and -2. Okay, well, now it says find the parametrization of the line of intersection. So just keep in mind when we talk about this parametrization of the line, then we need to know a starting point. We need to know some x0, y0, z0. And we need to know a parallel vector. Okay, so let's just start off by finding a few things that we know we're going to need. Okay, we know we're going to need to find N1 cross N2, so we might as well go ahead and start with that. Okay, so N1 cross N2. So N1 cross N2, by using our determinant formula, is just IJK and 3, here we got 3, -6, 2, and 2, 1, -2. Okay. So when we compute the I component here, we simply get 12 minus 2. Just verify that these were the right values. Okay, so we get 12 minus 2, which is 10i. Then we end up getting the j component. The j component, I'm going to apologize right here because I just looked back at the lecture notes and realized that I wrote one of these down incorrectly. So I'm just going to change that so you can follow along correctly. That was up here in the first vector. That should have been a minus 2z. And therefore, that would have affected the z coordinate to be negative 2. Okay, and that would come down here and change this to negative 2 as well. So I just want to make sure that we're staying consistent with what's in the lecture notes so that you can follow along there. Okay, so going back to finding the cross product. So in the I direction, we have 12 minus negative 2, which gives me 14 as the coefficient there. Minus, now we cancel out the j and we get negative 6 minus negative 4, or negative 6 plus 4, which gives me negative 2, so minus negative 2, or 2j. And finally, in the k direction, we get 3 minus negative 12, or 3 plus 12, which gives me 15k. So let's just look back to our diagram and see what that ends up demonstrating, right? So that cross product is really the cross product between the two normal vectors, the two red normal vectors, the planes. And that cross product we know is parallel to the line L. And in order to come up with a parameterization, that's what we needed. We needed to know what that parallel vector was. And so this parallel vector is the vector v in our parameterization. That's our parallel vector. Okay, well that's good. So why don't we go ahead and start to write out the equation of our line. So the parameterization of our line is going to be x equals, y equals, and z equals. Now we don't yet know a point on the line, but what we do know is that I'm going to be adding 14t for the x component. I'm going to be adding 2t for the y component, and we'll be adding 15t for the z component. Now the only thing we don't know is a point that lies on the line. So what we do know are the two planes. We know the equation for the blue plane and the equation for the orange plane, but we don't know any points that actually lie on the line itself. So the way that we could find that is just by setting one of the coordinates equal to each other. Maybe we set the z components equal to 0, or we set the y component to 0, and then we solve. So if we go back to our planes, let's just let z equal 0. So let's just say that the z component is 0. Remember, we only need we don't need multiple points. We only need any point that lies on that line. So let's let z equal 0. And if we do so, that means that 3x minus 6y is equal to 15. That's from our first plane. And for our second plane, if we set z equal to 0, we get 2x plus y is equal to 5. That's from our second plane. And so now we're saying that if z is equal to 0, what would the x and y have to be? And now this is nothing more than a system of equations. We can multiply this bottom equation by 6, which gives us the system 3x minus 6y equals 15, and 12x plus 6y is equal to 30. Add them together to get 15x equals 45, which implies that my x coordinate would be 0. Or I'm sorry, my x coordinate would be 3. And if my x coordinate is 3 and my z coordinate is 0, I could plug those into any one of the equations I want. I might as well plug it into the first equation, which gives me 3x minus 6y minus 2z, which remember we set equal to 0, is equal to 15. So if I subtract, we get negative 6y is equal to 6, and therefore y is negative 1. And so notice that that gives me the point, or a point, any one of the points, but I chose the point where z happened to be 0, and that gave me a point that was on that line of intersection, which means we can come back over here and recognize that my z coordinate is 0, my x coordinate is 3, and my y coordinate is negative 1. And I now have the parameterization for my line. The last application I want to take a look at here involves very similar to what we did in the prior lesson in finding the distance between a line or a point and a line. Now we're trying to find the distance from a point to a plane. So in this diagram here, you see your three-dimensional coordinate system, and you see this point S that lies off of the purple plane here. And our goal is to be able to find that distance from S down to the plane. Now, most importantly, we want the distance there to be orthogonal to the plane, or else it's not necessarily going to be the actual distance. You want the shortest distance from the point to the plane. So what we can do is we can pick some point that's actually on the plane, similar to what we did before. Let's call that, say, point P. And now we'd like to find the distance between S and P. Now, even though we can't necessarily find that distance, we can find a vector extending from P to S. And notice that at that point, you now see a right triangle. In addition to the point that's on the plane, if we're given the equation of the plane, we should also know a normal vector, because remember that that's just going to be the coefficients of x, y, and z. We refer to that as a, b, and c. So if we're given a normal vector and we want to find the distance from the point to the plane, what we could do instead is we could actually project this vector PS onto the normal vector. And if I do so, forming a right angle, then we should recognize that this distance right here is exactly the same distance that we're looking for. So the general idea here is that we're going to project the vector PS onto N, and whatever the length of that projection is going to be the distance that we're after. So we can say that our distance is equal to the magnitude of the projection of PS onto vector N. So we know how to find the projection. It's literally just the application involving the dot product. So once we find that projection, we could just simply take the magnitude of that, and that's our answer. Now, how do we find that? Well, if you remember what we ended up doing before, this distance formula was nothing more than just the PS dotted with N divided by the magnitude of N. But notice that we're actually finding the magnitude of that, but it doesn't really matter because of the fact that a magnitude of a magnitude is still just that number. Okay, so this is how we found the magnitude of the projection. If you want to go back a minute just to remember why, that's because this right here was being multiplied by N over n factorial. I'm sorry, n factorial, the magnitude of n. And so this right here was actually, as a whole, the projection formula. This was the projection. Maybe I should get rid of the equal sign real quick. The projection of PS onto n had this formula. But keep in mind that if this right here was our unit vector, then that means what's in purple is the magnitude. So this right here is the magnitude formula. That's the magnitude of the projection. Okay, so just to clean that up a little bit, that means that the D value that we're after is really just the dot product between PS and N divided by the magnitude of N. I don't know if that looks familiar to anybody, but it was very similar to what we did when we ended up finding the distance from a point to a line. The distance from a point to a line was PS cross V, right? And once we ended up having that, we took the magnitude and divided by the magnitude of V. Well, look at how these formulas are relatively similar. It's just that this one up here, the new one involving the plane, already has a scalar in the numerator, so I don't have to look for the additional magnitude. So I think we're ready to just do an example, and we'll finish this section up. Okay. So for this example, we're given the point S, and we're given a plane, but we're not given a point on the plane. So we don't know point P. So to find point P, we just have to think about how we could, how we could find any point that's on the plane. So really, we just have to let two variables equal some quantity. So why don't we just go ahead and let x equal 0 and about z equals 0. And if I set x equal to 0 and z equals 0, then that means that we have 3 times 0 plus 2y plus 6 times 0 is equal to 6. So if 2y equals 6, then that means y is equal to 3, which means we have a point P on our plane. Notice it doesn't matter what point we pick. We just need any point on the plane so that we could draw a line connecting it to S. We could have very well let x equal 0 and y equal 0 and found z. Or we could have let x equal 1 and y equal -3 in order to find z. It doesn't matter what you choose. You just pick something that's nice and easy. All right, so that means we need to find the vector PS. All right, so the vector PS is going to be 1 minus 0 in the I direction. Going to be 1 minus 3 in the j direction. And it's going to be 3 minus 0 in the k direction, which gives me the vector 1i minus 2j plus 3k. All right, so we have PS, but we don't have n. That's something else we're going to need. But remember that we technically do have n, because if we're given the plane, the coefficients tell me what the normal vector to the plane is. So I know that the normal vector is 3i plus 2j plus 6k, which means we're now ready to use our formula that we need. We could throw everything into the appropriate spots. So we have that the distance is equal to PS dot n. So we're going to take PS, which is the vector 1, -2, 3, and we're going to dot that with the normal vector. which is 3, 2, 6, divided by, and now we need the magnitude of the normal vector, which is the square root of 3 squared plus 2 squared plus 6 squared. All right, well, up top for the dot product, we get 3 minus 4 plus 18. And on the bottom, we get the square root of 9 plus 4 plus 36. Well, taking a look up top, 3 minus 4 is -1. -1 plus 18 is 17. The denominator we see is the square root of 49. So all we're left with is 17 over 7, and that is the distance we're after. So notice that what we've just done is an application that allows us to find the shortest distance from some random point in space to the plane. And we've actually used all of what we've learned in terms of cross products and dot products and equations of lines. This is now culminated in this problem essentially, because it's using all of the aspects that we've learned so far relating to vectors.